Let us talk about this problem. We are given two arrays which might be unsorted. Our task is to count distinct elements in both the arrays combined. For example, if you see these two arrays, the elements which are there in both the arrays are 15, 20, 5 and 10. Right? There are four distinct elements. 15 appears multiple times in both the arrays, but we need to count distinct. So our output is 4. Let's now see this example. Here we have again 4 elements 10, 12, 15 and 18. Let's see this example. Here we have 3 times here, 3 2 times here, but the one element is, there is only one element present in both the arrays and that one element is 3. So our output is 1. Now please pause this video and try to think of an approach that takes two arrays as input and returns count of distinct elements in both the arrays. Let us first talk about a naive solution to solve the problem. The idea is simple. We initialize our result as 0, right? And we create an array distinct to store the distinct elements of A and B both. And this is the array we are going to use to check if an element has already been seen or processed or not, right? So what we do is we initialize this array as empty. We traverse through elements of array A, right? And if this element is not there in distinct array, we insert it into the distinct array, we append it into the distinct array, right? And we increment the result by 1. So 10 is inserted here, result becomes 1. Then 30, it's not there in the distinct array, we insert it into the distinct array and increment the result to 2. Then 10 is present in the distinct array, so we are going to keep the result as 2 and we are going to keep the distinct array as 10, 30. So after we have processed the array A, our result is going to be 2, our distinct array is going to contain 10, 30 distinct elements of array A. Now what we do is, we process array B, and when we process array B, we again do the same thing, the same similar steps, right? We traverse through every element of array B, we check if it is in array A, it's not, we'll add 5 to the array distinct, right? And then we'll increment the result to 3, and we'll check for 10. 10 is also 10 is present here, so we'll not process it, we'll simply ignore it. 5 is also present here, we'll ignore it. So finally our distinct array is going to contain these 3 elements and our result is going to be 3, and which is correct output. The result is correct output for these two arrays. The array distinct is there to just help us in figuring it out what elements have already been processed, right? That's the purpose of distinct array. Now what is the time complexity of this? See, there are mainly two major steps where we, in this step, we traverse through array A. So we are going to run a loop m times, and inside this, we are checking if the element is present in the distinct array or not. And distinct array might contain all the elements of array A. So it's upper bounded by m into m, right? See, initially there would not be anything. For first element, you will not traverse distinct. For second element, you might have to traverse once. So it's something of m into m plus 1 by 2 kind of thing, right? Which is big O of m square. Now, in the step 3, what happens is we have m elements already. M is the size of array A, right? N is the size of array B. And we traverse through array B. And we might have at most m plus n elements in the distinct array, right? If all the elements are distinct in array A, say you have 10, 20, 30 here and then 40, 50, 60 here, right? In that case, we'll have all m plus n elements at the end. So the upper step, this step also, the fourth step is also upper bounded by n into m plus n. That's where upper bound is useful. Instead of doing the exact mathematics, we find an upper bound. Okay, that's going to be the maximum size of distinct, right? And we are going to traverse through every element of B, right? So we use an upper bound here. So that's the time complexity, upper bound on the time complexity of this solution. And this looks high, it's quadratic, right? So the idea is this, instead of using distinct array, right? Because the operations that we are doing on the distinct array are insert, right? We don't need any order or anything. We just need to insert certain items and then we need to search certain item present or not. And when you have these two operations, hashing is the data structure, right? It inserts an item in constant time, it searches an item in constant time. So instead of using a distinct array, we can use a hash here. Now please pause this video and try to write down a complete solution that works in linear time. Let's now talk about the efficient solution, and the idea is to use a hash table, unordered set in C++ and hash set in Java programming language. We create an empty hash table, a simple unordered set in C++ and a hash set in Java. Then we traverse through all the elements of array A and simply insert them one by one into the hash table, right? And the unordered set in C++ and the hash set, they work this way that when you try to insert something which is already present, they ignore it, right? So the hash set is going to contain 10, 30, right? And now we traverse through all the elements of array B and do the same thing, insert them into the hash table. So it's going to ignore the elements which are already present, 10 is going to be ignored and our hash table is going to have 10, 30, 40. Now at the end, what all we need to do is, we need to return size of this hash table, that's all, and we are done. Let's analyze the time complexity of this. So this step is going to take theta m time, if m is the size of array A. This step is going to take theta n time, and this is constant operation. These two are constant operations. So overall time complexity is going to be theta of m plus n, right? And how much auxiliary space we need? We need big O of m plus n. Why am I using big O notation here? See, it might happen that you don't have all the distinct elements, you have too many repetitions, right? The auxiliary space will be exactly theta m plus n when you have all the distinct elements like 10, 20, 30, 40, 50, then everything will go into the hash table. In other cases, it will be less than m plus n space. So that's why I have written big O of m plus n. Now please pause this video and write down complete implementation yourself. Here is implementation of the efficient approach. Here is C++ implementation and there we have Java implementation. So both the functions take two arrays. We use unordered set. In C++, we can create an unordered set using array elements directly. So that's why I have used the constructor syntax. And this unordered set H is going to have all the distinct elements of array A after this step. In Java, we first create an empty unordered empty hash set. Then we insert all the elements of array A one by one. See, in Java, if you have integer array, which is a wrapper over int, right? Integer is a class, right? So if you have a class objects, right, then you can directly create a hash using array elements like you can in C++, right? There is arrays.asList function that allows you to treat the array as list, right, without using an auxiliary space, treat the same array as list, and then you can construct a hash set from the list, right? So this, if this was an integer array, we could have shortened the code like C++, but it's an int array, that's why I've written add one by one. Now we traverse through array B and add all the elements of array B in the hash set, right? And at the end we return hash size here in both the places. And we have already seen a dry run, initially empty, then array A elements, then B elements, and at the end we return the size, which is 5 in this example. We have total 5 elements. Time complexity also we have discussed. It's theta of m plus n, theta m for processing array A elements, theta n for processing array B elements. And auxiliary space is big O of m plus n, because that's the maximum number of elements you will have in the unordered set or hash set.